Okay, so without any further ado, I'll start off with a short demo. I hope. Okay, so I'm going to start with a very quick demo. Bear with me for a few minutes. In my demo, I have a program called Naive. I'll make the font a bit bigger. Okay, so what this program stands, it's a very generic, simple program. It represents any. So I think of it as, for example, as a service running on a server which gets requests from users and processes them. But it really could represent any user application. So what it does is the main function passes its argument argc-argv to the do-work function. The do-work has an internal buffer, and what it does is it iterates through every one of the arguments which are presented to the application, copies them to its internal buffer. It simulates returning memory to the user. In essence, we don't do anything here. And then it processes the argument. And for the purpose of the demo, I simply print that we're processing the data, sleep for a little bit, and that's what we do for each one of the arguments. And when we finished, we return to main and call done, which basically just tells us that we're done. Okay, so if we run naive with hello world, it will look something like this: processing data hello, processing data world, and done. Just for the consideration of convenience, for what I'm going to show you a little bit later, I would like to just pass the arguments to the naive program in a slightly different way, not directly off the command line. What I'll do is I'll write a script, which simply outputs what is to be the input parameters for naive. So it will look like this. I'll make it executable. So if I run input sh, do not call it input sh, print printf. So it outputs hello world, which are going to be my input parameters, and now I can run naive like this. I call naive with the output of the execution of input sh. And it looks like this. So this is equivalent, and I just do it for convenience. One more thing I want to show you, again, pretty basic, trivial, is before I move on to more interesting things, is the process tree associated with this executing shell. So for that I need the PID of the executing shell. I did that by issuing $. So the process ID is 4423. And what I'm going to do is I'm going to use the PS tree program, which is a nice program that shows you all the processes in the system and a nice tree hierarchy. I'll do it with, but I'll just show the branch relevant to the executing shell. So for that I do -sp with the PID I'm interested in, 4423. And there we get our hierarchy. So we have the system D process, which has a child process console, which has a child process bash, which is our executing shell. I'll just highlight that for nicer. Something like that. Okay, there we go. Okay, so up to here everything is as expected, and of course if I run naive, I'll give it a few more arguments so it runs for a little bit longer. So of course if I run naive and I query the process tree, then of course as expected we get naive as a child process of bash. And when it completes its running, then of course there's no more naive process. So all this is as expected and very simple and naive. What I'm going to do now is I'm going to give naive slightly different input. And the input I give naive is this. Okay, so let's see what happens when I run naive with this input. Sorry?
Bigger than 256.
Okay, it's done.
It's a Unicode, no? No.
No, sorry. That's what I'm doing. Okay, so let's run naive with the new input. And as you can see, we get some stuff on the screen, and we seem to be running back in the shell. But I'm not sure it's back in the shell. The shell that I'm running now looks a bit different than the shell that I was running before. Let's see what happens if we look at its PID. And we actually see that we're running a different shell. Okay, we're not running the same shell that we were running before. And if we look at the process tree, then what you see is that Bash does have a child process. It's the shell that the new shell, no sign of naive anywhere. And if you look carefully, you can see that naive did start running. It wrote that it's processing this data, the strange data that it provided, but we never reached the done statement. And something strange happened here, and now we're running a different shell. So let's take a more careful look at this input, see what it's all about. I have to go like this. Okay, so this is the input I provided the naive application. And primarily this input is comprised of two main parts. This part of the input, what it does is it's responsible for exploiting a vulnerability in the naive application and gaining control of the process flow. This part of the input is responsible for doing what it is I want to do once I have control of the flow. In the case of the demo, I chose to spawn a shell. I could have chosen to wipe the hard disk. I could have chosen to send mail myself private keys or certificates from shadow files. And of course, if naive had been running as a root process, then I could have basically done anything I like. And daemons on servers tend to be running as root. Even if I weren't running as root, there are other attacks which are designed at gaining root access. It's not the topic of this talk, but I'd be happy if someone gave one like that at some point. But anyway, as you can see, it's very this is very malicious input, and this is what it does. What I'm going to be doing throughout the rest of this talk is, firstly, we'll fully understand the vulnerability, okay, how it works, or what the problem is. And I will be basically showing you how to, without a lot of pre-knowledge, how you can quite easily create this kind of input to the particular vulnerability. I didn't have much pre-knowledge in assembly programming or machine programming, and I'll show you that it's actually, you don't need too much of that. In the end, I'll just run through a couple of the defenses that we have against these kind of attacks today. So that's what we're going to be talking about. So I'll start off with a quiz. This is the quiz that I actually asked Daniel, and Daniel's one of the few people who solved it nicely. So in the quiz, I have a main buffer initializes a buffer with a string ABC and passes it to function f. Function f receives a char pointer src, a source, copies it to its internal buffer dest, which it intends to print by calling printf. So the very diligent and careful engineer who wrote this code doesn't trust the people, whoever's calling f, so he made sure to put a null terminator at the end of dest, so the printf doesn't get messed up, and he calls f. Calls printf. Once that's done, return to main and we exit. In the quiz, we have another function, g, which simply prints in g and calls exit. What you have to do in the quiz is to get g to run. There are a few constraints, of course, otherwise it wouldn't be that difficult. The constraints are as follows. The only place you can write code is over here. And of course you cannot call G directly.
I answer it, or?
Yeah, go ahead.
So the main problem is that the str copy is not considering the desc length, it's only considering the source length. Since you can, since buff is 40 size, the array size of buff is 40, you can put after ABC the pointer to another function, then you override the stack, and then instead of F going back to main, it will go back to G. But how to do it, it's a little more sophisticated. The solution is to use strn copy.
Correct.
Not strn copy.
Absolutely correct, and a full answer. The rest is technicalities, which I'll show you how you actually look at.
But you also have to return from G and go back to.
And there's an exit out of
But
That's already more complicated.
okay. But as you notice, G has got a call to exit, so we don't have to. Okay, but very good, Rafi. That's the whole story, and basically that's what we're going to be doing. So before I go into the details, I'm going to run through a few things which I just want us to be aligned on, because to serve us throughout the rest of the talk. I'll try and run through it quickly, because I'm sure quite a bit of it is stuff that we know to certain different people to different extents. So I'll be looking at memory quite a bit, and I'll be using GDB. GDB has the notion of artificial arrays, and the way GDB presents an array is just to you provide it the first element in memory that you want to print, and then you write ampersand how many such elements you want to print. First element at length. So for example, if we have an unsigned long array of size 2 with these two elements, the first example, we print /x. /x is for hex representation at 2, and we get two unsigned longs presented as an array. Equivalently, we could dereference array as a pointer, and $1 and $2 are equivalent. I could, if I wanted, look at array byte for byte, in which case I would cast array into an unsigned char pointer, dereference it, and then ask to see the first 8 such elements, in which case I would get what I see in $3. Now you'll notice that the first element in $3 is actually the least significant byte in the first element of the unsigned long array. And the second is the next least significant byte, and so on, all the way to the end. Of course, the reason for this, for what we see here, is that we are running on a 64-bit little endian system. Now, we're always talking about big endian and little endian. We often get very confused, so it's important for the purpose of this talk that we're straightened on what that means. Significance of being on a little endian system is that the lower significant bytes reside in lower addresses in memory. So if we have this value, if you look at the memory, this is how it is going to be, how it's going to live in memory. But if we ask to look at it, at that piece of memory as an unsigned long, then it will present it as an unsigned long, as a number. So there's the byte perspective and the long perspective, or multiple byte construct perspective.
Can you return what is the stack reference to?
What do you mean?
I just addresses.
Just addresses on the stack. Just addresses on the stack. Okay. Okay. Objdump. Is there anyone who hasn't used objdump? Doesn't use objdump. Okay. So objdump is a very it's an excellent program for giving a lot of information about binary object files or executables. I like using this -d for disassembly. It's very convenient, at least at the beginning stages, to use -s because it also inserts the code. And if you want to see certain sections, like the data section or the text section, then you can also limit it to specific sections. So if we look at an example output of running objdump on the quiz main function, then the kind of information you get there is the offset of the main function from the beginning of the object file in this case. You get offsets of each instruction within the code. These offsets we will find later on during the talk very useful, because I will be wanting to jump over certain blocks of code, and when I have the offsets here, then it's easy for me to calculate how much I need to jump. Not mandatory, but it definitely helps. We get the source inserted in the code due to the -s flag, and we get the assembly inserted in the code due to the -d flag. And the most important part of the object dump, which is what I'm out to seek to get here, is the equivalent machine code instructions. Equivalent, each assembly instruction's got its equivalent machine code instruction, and that's what we're going to be using. These are the numbers that you saw in the input to naive SH. By the way, if there are any questions, I won't be stopping to ask if there are questions. If there are any questions, just stop me along the way, okay? ABI. An ABI is a document, it's application binary interface. It's very similar to an API, but it's the interface between two program modules, one of which is usually an operating system at the level of machine code. In short, the ABI defines stuff like what the different registers on the machine are going to be used for, what the function calling conventions are. Calling conventions, not coding conventions. Calling convention is the sequences of calling functions, how that's done. And so it's a very platform-dependent document. So, and for understanding what we're seeing on the stack, it's useful to consult the ABI, the AMD64 in this case ABI, to understand how the registers are being used. I'll spare that from you guys now, but I will be talking about a couple of registers throughout the talk, so I'll just mention them. You don't have to remember them because I'll be coming back to them all the time. The first one is the instruction pointer, RIP. At any given moment, the instruction pointer holds a value, which is the address of the next instruction for execution. It has 2 pointers which are responsible for stack management, managing the function stack frame, the RBP, which is the base pointer, and the RSP, which is the stack pointer. The AMD64 ABI states that the first 6 numeric values passed to a function are passed via registers. If any of the arguments are non-numeric or you have more than 6, then they have to be passed by a stack. In our talk, I'm only going to be using 3 numeric registers, so I only mention the first 3. The first argument is passed in the RDI register, the second argument is passed in the RSI register, and the third argument will be passed in the RDX register. And we have general purpose registers. I'll mainly be using RAX, but RTX does appear in one example, so I mentioned it here too. Mainly we use RAX as a general purpose register. So these are what we're going to be using, and I'll be coming back to them quite a lot. Just one more thing I'll mention is that on this platform, all the registers are 64-bit long. It is possible to reference shorter segments of them just by calling them different names. So instead of RBP, I can use EBP to access the least significant 32 bits, BP for the least 16 significant bits, etc. I won't be using this a lot, but every now and again you may see a reference to EBP or EDI. You'll know what they're doing, what I'm doing. And then we have the calling conventions, which is basically the sequence taken when we call functions. So I want to introduce that to you now quickly. So initially the instruction pointer will be holding some address of an instruction in main. We'll be running in main, and at the same time there will be a stack frame defined for the main function, which are defined by the RBP and the RSP pointers. The RBP points to the top of main's stack frame, and RSP points to the bottom. When main is called, the arguments to main, in this case argv, argc, are copied from register to stack at the stack pointer, more or less, maybe a little bit higher, but starting at the stack pointer in principle. And extra space is reserved on the stack for local variables of the function. Now, I'll just mention one thing, a question that will no doubt come later. All my examples in this entire talk about the case when we have no optimizations. When the compiler compiles optimizations, then things work a little bit differently. Essentially, what I would have to do to conjure this kind of attack is the same, but I would be using different offsets. I maybe have a slightly different sequence of instructions, but basically the work would be the same. It's just simpler to understand without optimization, so the entire talk is without optimization. At some point, the instruction pointer will reach the call to F, at which point implicitly the return address into main is pushed on the stack. So if you notice, if the call address, the address of the call to F in main is at 400.681, then the address pushed, the little Indian format, is 400.6.8D, which is already the next instruction. And by pushing, what pushing on the stack means is that the stack pointer is decremented by however much it needs to be decremented, size of address in this case, unsigned long, and the value is placed at the stack pointer's new address. From this point on, we're in the F function, and what happens next is that the base pointer, the previous base pointer, gets pushed as well. Okay, so if you see the number that ends here with D4F is pushed onto the stack as well with D4F. The previous stack pointer is assigned the current value of the stack pointer, and then the stack pointer is decremented to create a new stack frame for F, and again the arguments are copied from the registers into F's stack frame, and space is reserved for its local variables. When F returns, it's very easy to reproduce the previous state in main. We know the previous stack pointer was 2 addresses up from the current base pointer. We know that the return address is stored 1 address higher than the base pointer, and the base pointer needs to restore itself to the address on the stack at which it's pointing now. It's very easy to return things to their previous state when we finish from F. So that's how the stack is managed. Okay, I think I'll move on. Yeah. Okay, so let's see what happens in our quiz. Okay. So this is our stack initially, and initially we'll be running in main. So there'll be a stack pointer for main and a base pointer for main. By the way, despite what I said previously, are there any questions till this stage? Okay. Okay. So when main gets called, its arguments get pushed on the stack, and place is reserved for its internal buffer. Okay, so at the stack pointer we have the argv. The argc is an int. It was an int, 4 bytes. In little Indian representation, is stored at this address, and here we have ASCII A, B, C, 61, 62, 63 with its null terminator. The rest of the buffer also happens to be null, zeros.
Aren't the stack and the base opposite? Shouldn't be in opposite places?
The stack and the base both are the stack pointer and the base pointer are used to define the stack frame.
Yeah, so the base remains throughout the entire function, yeah. And the stack.
The stack may move. The stack is at the bottom. The stack doesn't move unless there are pushes or other. Okay. Okay. So when F is called, then a new stack frame is opened for it. The return address into main is pushed. The previous stack pointer D4F0 is pushed. And the arguments and the local variables of F are pushed onto F stack. So this is the argument. You see it's D4C0. D4Z0 is exactly the starting address of the mains buffer. And this is currently garbage because moving for the str copy. Okay, and the rest of the bytes on the memory here are not in use. Okay. Now, what we're going to be doing is exactly as Rafi said. The idea is to create a stack overflow, and what will we want to overwrite here? The return address. Okay, so it will look something like this. So that's the idea. Okay, where is all this going to come from? It's going to have to come from here. Okay, that's where it's going to be copied from. Okay. Now the fact that the engineer put a 0, null terminating 0 after the str copy over here doesn't help because the damage has already been done. By the time he does that, the address has already been overwritten. If anything, it will simply hide the bug. of the problem. Okay. Let's just see how that works. Diagram. Yeah, so this is going to be the. So this is the answer, of course, to the quiz. We fill up a buffer with just non-zero bytes until we reach the place where G's address needs to reside. And after that, we will put a null terminating 0 because we want to stop printing after we've overwritten the address. Okay, so it will look something like this.
Why do you have to fill? I know.
Question? Okay. And if I run quiz, okay, so we have ABC printed, but then we also get in G. Okay. Okay. Let's move on.
Why do we have to fill the first and the second element?
So the SDR copy will copy.
We're going to start copying. This is the location, this is the address of dist. Okay.
Mm-hmm.
I was going to show it to you in GDB, but we're a bit short on time, so I won't. If we looked in GDB and we seek to see what's the address of dist, we will find that this is the address of dist. And what's going to happen is that the data at this address, that means from here, is going to be copied from here, starting at this address. We wanted to copy, but not in here. We wanted to copy, and we want G's address to be over here. Okay, so the only thing that's important about these F's is that they're null terminators. They could have been any value.
Okay.
Okay, and after the address of G, I will want to stop, so I do put a 0 over there. Okay. Okay. So that's the gimmick. That's the trick of how we gain control in this attack. Now I'll talk a little bit about spawning a shell and how we get to that. So this is a program that spawns a shell. Okay. We call execve, and execve receives 3 arguments. The first argument is the path to the executable we want to run. It's the second parameter is an array, an argv array, which is null terminated, and the first argument will always be the first argument, which is the path. And the third argument we will not be using. It's an optional key value, null terminated key value array of environment variables that we might want to pass, but we don't need it, so we'll just let it pass. And if I run it, okay, so this is the code. Okay, so this looks a little bit like where we want to get to in the end. Okay. Okay. Okay, what I would normally do at this stage is what am I doing wrong? Minus ES text minus section. Okay. So what I have here is pretty much what the implementation of the execve program translated into assembly. I see the assembly instructions that that implement it, and the corresponding machine code that implements it. Let's see what corresponds to what code. What I'm going to do is, let's go through this. I'll do it in a presentation because it's just easier to see. and analyze what's going on here. So initially, main is called. Main is called from a libc function called start, which GCC implicitly links in when we build a program for the C runtime environment. So the previous stack pointer would be pushed, and then we call main. Once in main, we push the stack pointer, as we saw before. We move this previous stack pointer to equal the current stack pointer, and then we decrement the stack pointer to open a new stack frame for main, okay, as we said before. We then move the first arguments, which are argv and argc, rdi and rsi, to their location on the stack. First the argc argument, and then the argv argument. Okay, this is called the prologue of the function. Okay, this is before any code has been written. The rest are not used at this point. Next, we set up the local variables for main. Okay, so we're going to move this. Okay, this is the pointer to /bin/sh. Okay, we're going to move it into a location on the stack. It's going to be this location. This is also going to be our array, which is the second input for execve. Okay, that's var 0. You can see it in the code. And var 1, which is the null, 0, is put immediately afterwards. Okay, so this is our array. Okay. Next we call execve. So to call execve, we need to set up the registers with its input parameters. Because we're not working with optimizations, the compiler doesn't do it in the most efficient way. It uses temporary registers in the mean, intermediate registers. But firstly, it copies firstly it copies the address of the string, first argument, into RAX. Next, it copies the address of the array into RCX. Okay. Next, we move the terminating 0, the null, the third parameter to execve, into the third register RDX. Okay. The second register RSI for the second argument receives the address of the array, and the first register RDI receives the address of the actual string /bin/sh. And then we perform a call to execve. Let's see what happens in execve. Now, execve is slightly different in the way it's compiled. Execve, all it does is moves the value 3b into EAX and does a system call. That's all it does. And that being the case, there's no point in creating a stack frame for it, copying values from registers onto the stack, which will want to immediately copy back into the same registers to call syscall. So even though we're running without optimizations, the compiler doesn't do that. It moves the value 3b into EAX. Anyone got an idea what 3b is about?
I guess I will take a wild guess that each system call the kernel gets like a opcode and translate it to what it
very offset. It's the ID, it's the number that represents this particular system call.
action.
And if you look at include X ASM you're in 64-bit. We have all the system calls with their numbers. If we look for execve, we have 59. And hex value of 59.
It's like index to an array.
Sorry?
It's like index to an array.
Correct.
The opcode, yes.
Okay. So we set up the EAX register, which the kernel will query when we start running in kernel mode, with the value 3b and equal system call. Okay. The kernel will then look at registers RDI, RSI, RDX, and do its thing. Okay, so we saw this. Okay, so I'll just highlight the exploit strategy, and then we'll start talking about how I actually get to the input that we saw earlier. So we have the text section down here somewhere in memory. We have the stack somewhere up here in memory. Initially, the instruction pointer is running somewhere in main, and up here we have main stack frame. Okay. At some point, we reach the call to F. The F's return address is pushed on the stack, and it points back to somewhere within main. Okay. Next, we start running within F. RIP points to an address in F, and a stack frame is open for F. And what we do at this point is we override the memory with our input. Our input will consist of two parts. The first part is the implementation of execve in assembly, and the second part overrides the return address and sets it not at the text, not in the text section, but just before our or at our execve code. Our execve will execute, and we'll have shell running. Okay, so far so good. Okay, when we return from F, execution resumes on the stack. Okay, so we had our C code. What I'm going to do now, and again, I'm looking from the perspective of someone who's not a very proficient assembly coder. So I'll take the C code, I'll base what we saw base what I'm going to do now on what we saw in the ops dump, and I will write the same function in assembly. Okay. The idea is that if I have the assembly code working, it's very easy to then very easy then to convert it to machine code, because I have that one-to-one correspondence in the opt dump. So this is a design or the plan of how my code is going to look. Okay, it's kind of pseudocode. So at some point in memory, I'm going to have the string -h, and I put it in memory with the .string directive. What I'm going to want to do is to move the address of this string, which I don't quite know yet where it is in memory, but I'm going to want to move the address of the string into the base pointer -10. -10 hexa, that's -16 bytes. That's going to be the beginning of my array, which I provide execve. I want to terminate the array, which is the next address, RBP -8, with a null terminating 0. Okay. I'll set up my the registers for calling execve. So I'll put the address, the content of array 0 in RDI, the address of the array in RSI, null terminating null for the third argument in RDX. I'll move 3b into RIX, and then I'll do a system call. So basically, this is all I really need to write in assembly. It looks pretty simple. The problem is I don't know the address where /bin/sh is going to reside in memory. And the way I'm going to solve that, any ideas how one can resolve that? How can I find the address?
Base point. Where the data sits in the stack.
Then it's not necessarily going to be in the stack.
Can you just declare an argument, hold it or something, and then you can know its address?
I don't want to put arguments in. What's an argument? An argument is reserving space on the.
This is part in the code.
Possibly. Possibly you could do that. It's a lot more work because you have to decrease the stack pointer. You have to write stuff into there. So there's a nice trick to it. And the trick is called jump and call back. What I just said, this is what I presented a second ago. What I will do is I'll insert before I start, I'll insert a jump instruction to just before the string directive. And just before the string directive, I'll have a call which will take me back to the next instruction. How does that help me? Do you remember what happens when I do a call?
In the stack.
The return address gets pushed on the stack. In this case, the return address, if I'm running at address 8, for example, the return address will be address 9, which is actually the address of the string.
And you need it because the string is put in the code and not in the stack, the string itself, right? It doesn't exist on the stack, but in the part of the code. For
Even if it did exist in the stack, and ultimately it will exist in the stack, I don't know the exact address. Okay, and this is still, I don't need to know the exact address. Okay. Okay, so let's see how that would work. So if we look at, we follow through the code and look at what happens at the stack at the same time. So I do a jump. Instruction pointer is at instruction 0 at this point. I jump to 8, and I call back to instruction pointer -7. This is something that you can do with AMD 64-bit architectures. And because I did a call over here, the address of the return address, in this case string, is pushed on the stack. Okay. And initially the stack pointer and the base pointer were at the same point. The pushing decrements the stack pointer by 1 and pushes the return address. Okay. I then jump back to the next instruction, which I actually don't need anymore. I don't need to move anything into RBP -10 because it's already there. So let's look at how it will, the revised version of how it will look. I will jump to instruction 7. Okay. The stack pointer, the return address will be pushed onto the stack. I will call back to instruction number 1, and then I will continue as I planned before.
How do you know that the string is after the call? Because it's the last command.
Yeah, this is because this is text. Okay, these are instructions running.
You define the string right after the call. That's how you know the.
Yeah, actually, I defined the call right before the string. So,
That's optimization skills.
Okay.
I carefully chose the position of the call to be just before the string. Okay, so I set up my registers exactly as before, and a call system call. Let's just see what that looks like. Okay, let's make it 05. So this is the code. Okay, there are another 2 instructions. Actually, I just set up the RAX with how much it is I want to jump or call back. The RAX register with how much it is I want to jump. And then I perform the jump to RAX. And actually jump to this location where I set up RAX again with by how much I want to call back. Okay, and then I call the address in RAX. So this is, for the rest, it's exactly the same as in my pseudocode. Okay, so here's setting up a 3B system call, and if I run it, it works. So now the next stage is to translate what we just did into machine code. Okay. For convenience, this is, again, I'm developing this shellcode. It's called a shellcode. Okay, so I'm developing the shellcode. So just for convenience, I'm going to put the shellcode into an array, and I actually don't want this on the stack because it puts noise on the stack, and I want to understand what's happening on the stack. I'm going to move this array out of the stack, so it doesn't run within main. And the way I'm going to trigger it initially, what I want to do now is verify that my machine code is working properly. I'm just going to overwrite the return address using, I'll exploit the ret value and calculate where the return address has to be. And I'll just overwrite it with the address of my exec.ve just so that I can trigger the code at my exec.ve and see that it works properly. And it's very useful to also at the same time hold the assembly code which corresponds to the code, to the machine code in my exec.ve. So I'll put that in the code as well, and I'll toggle between running the assembly version and the machine code and the equivalent machine code version with an ifdef. Okay, so if it's undefined, it's the machine code which will be running, and if it's defined, then it's the assembly code that will be running. Okay, so it's very convenient this way. If I want to make something doesn't work, I can make a little change in the assembly and also make a little change, see that it works, and then try it out on the. So that's the technique. And this is having translated instruction per instruction, as you can see here in blue. This is the instructions that I ran before. So instruction for instruction, I take from the objdump output and I put it in my execv. Okay. So let's do that and see what happens. Okay, so this is the code. Okay, so the assembly is what we had before, but we will now run the myexecve version, which is this. What's going to happen? Oh, something didn't work. So why did it not work? I don't know if you know the tool readlf. Readlf shows you a lot of information, other information about the executable, how it's organized, not the actual code implementation. And if I run readlf on the naive app, then I'll get this output. I'll show you. Readlf. Okay, so what we get here is basically the organization of the ELF, the executable file. We see here all the sections. For example, there's the text section, and it states the offset from the beginning of the executable where the text section starts, its length. There are a couple of flags. Okay, I'll also have my execve will also appear here somewhere. Okay. You'll see that my execve, you'll notice that its address is 6CA0 something. This is its address in memory, virtual memory, of course. So let's remember 6CA0. If I look for 6CA0, and then there was an A afterwards. So it clearly resides in this at the section starting at this address, and that section is the data section. Okay, that's where it resides in memory. Okay, so this is the text section, and this is the data section. My execve resides in the data section. By the way, it says so in readlf as well. It has this 25 showing that it's in section number 25. Okay. Okay. Now, if we look at the flags that each one of these sections has, you'll notice that the text section has got an AX, has got flags AX, allocate, and execute. The data section has write and execute permissions. One of the principles by which code is organized and permissions are granted to different sections is that you never have write and executable permissions in the same section. It's called W XOR X. So naturally, if our buffer containing the code resides in the data section, it will not be able to execute. Okay, hence we get a segmentation problem. Okay, so what are we going to do about that? We need to put it in the executable part. So the way we're going to do that is simply put it in the executable in the text section. Okay, and the way you do it is by using the attribute section text. I just defined it to call it malicious, and I put my execve in that. Sorry?
Didn't know that there's this attribute.
So you learned.
Would other section work as well, like putting it with malloc?
Good question. There may be other reasons why it doesn't work, but it should. I mean, if it is executable permissions and there's enough space for it, don't see any reason why not.
Yeah, what I mean in essence is that there's a difference if you put it literally the string or if you put it in malloc or so is this the only case where this happens when it's in the global part of the code and then it
We'll
will
see.
be in the data section?
We'll see.
and this
We'll
is
come
the
back to
reason.
that. Keep that question, we'll come back to that, okay? Okay, so now I've changed it, I've added the attribute, the text attribute, and now if I run it, oh, it all works nicely. Okay. And if I read ELF again, not this one, where is my execve located? Insert. Okay. Okay, so after fixing it, my execve now is in the text section with executable permissions. Okay, so now we've got machine code running. I got my machine code to run, I ran it off the array. However, the ultimate goal is not to trigger it the way I did, but to exploit strcopy. And if that's what I'm going to be doing, then there's a problem with this code as it is. Can anyone see what that problem might be? I'll give you a hint.
What was the?
What's going to happen when I use strcopy to overwrite the stack?
It will stop after the null.
It will stop after the first null. My exploit will not work if it has terminating zeros in the middle. Okay, but these are the instructions. These are the instructions as they appear in Octane. So I have to get rid of them somehow. Okay. So let's see how we can get rid of null terminator. A few techniques which I use. The first is to take x, add a constant and remove a constant. So for example, if I had this instruction which has a couple of zeros in it, instead of using 0x21, I will use this number and then I'll subtract it. I'll subtract the 1. Okay? No zeros in the resulting machine code. Okay. Another technique I could use is by using SAW. Okay. So if I want to move 0 into a certain location and the corresponding instruction contains zeros, I can first SAW the RAX register, for example, and then move the RAX into that location. No zeros in the resulting machine code. Okay. And the third very simple technique is, if I already have put a 0 somewhere in memory, I can use that again. So if I want to move a 0 into RDX and need to get rid of the zeros in the machine code, I can just use 0 which I've previously placed on the stack in a different location, and I happen to know that it's there, and I can move that value into RDX, which I also found useful. Okay, no zeros in the resulting code.
Again, can you repeat this last one? The reuse?
How is it 4 times?
That's just the instruction. That's the instruction, because some of these are.
It's like
Why is it 4 zeros here?
No, yes. It's 4 zeros because that's the.
I think that's the 0 that I'm moving. RDX. Yeah. I didn't actually go into the actual meaning of each instruction, but clearly these zeros correspond to the 0 in the same instruction. Okay. At least some of them. Okay. Any question here? So if assume that in RSP plus 8, I previously put a 0, like in the previously I know that at that location on the stack there is a 0. So if I want to move a 0 into RDX, I can say, okay, take the location, copy from a certain location where I previously put a 0, copy from that location into the register RDX.
Okay. But the problem is that during the copy we don't want to see the zeros. So you just
We don't see the.
how do you do the translation later?
This is the new instruction. Oh, well, so for example, this could have been the previous instruction. So this move Q instruction will be replaced by the XOR and move Q. Okay. Now I know that at RSP plus 8, I've got a 0.
Okay.
Now if I want to move a 0 into RDX, the next instruction can be move RSP plus 8 into RDX. Okay, so these are 3 techniques which I can use to eliminate zeros. So having done that, my code will be modified and will look like this. I just have the null terminator at the end of the /bin/sh, and you can see that I've added a few more instructions, usually subtracting instructions, and instead of using, for example, 28 here, I would have used 1111 with a 39, and then subtract the ones. Okay, and we do that again. Instead of 3b, which is actually 00003b, I do the same trick here as well. Okay. Okay, let's just take a quick look at that, see if it still works. That also was very important for me while I did that, of course, to every stage, to see that things still work. Okay, so it wasn't this one. It's this one. Okay. No zeros except for the terminating zero of the /bin/sh. Make. And everything's still working. You guys still with me on the line? It's very quiet. Okay.
In line.
Yes,
In line where he is.
So far so good? Everything okay?
yes.
Okay. So let's continue. Okay, so ultimately I'm actually not going to be wanting to execute from within the text section. I did this mainly for my development, and it was throughout the development, continuously looking at the main stack frame to see that things are as you expect, and you don't want to dirty it with this big myexecve buffer, so I moved it out of the stack. But ultimately I'm going to want to start executing the code on the stack, okay, not from within the text section. So what I'm going to do is I'm going to now, having done that, I'm going to move myexecve back. Now that I've got myexecve set up as I want it to be, it's debugged, it's working, I'm going to move it back into the onto the stack and move it back into main. Okay, so let's do that. So here's the new code. Okay, so I've moved myexecve as it was before. As it was before, I've moved it back onto the stack, and now I'm going to try and execute it from the stack. What's going to happen?
Not going to work.
Why?
Because the stack is different and the tuples or the code area is changed.
Yes, I get a segmentation fault. Let's do readelf again. Okay, so yeah, again I get a segmentation fault. Let's see what's happening here. Okay, so by default, GCC marks executables and shared objects as not requiring stack execution. Hence, by default, the stack is not executable. Okay, it is possible to exclude the stack. It's like minus minus. It's impossible to exclude the stack header from being marked this way. And the way we do it is with a very simple tool called execStack. ExecStack, you can either use -s to set the application as requiring executable stack, or you can clear with the -c the executables and set it as not requiring an executable stack. And you can query the executable stack permission status with the -q, in which case it marks it with an x as if it's enabled, and a minus if it's disabled. So of course, if I run exec stack on naive, what am I going to get?
Minus.
A minus. How am I going to set it? How am I going to set it? With the minus S. And if I check it again, now there's an X telling me that the stack is now executable. And if I now run naive, it works. Okay.
What calls this is the line for call?
Sorry?
The line for call is the one that calls
No,
it,
no.
so they run for the run
The
exit.
fact that you're trying to run code, the fact that you inserted an address on the stack into the instruction pointer.
And how does it usually work when I do in my code run shell? How would it work?
What do you mean?
When I write a C application that calls exv, how?
No, then the exv runs from the text section.
Ah, okay.
Okay.
Not from the stack.
So written ELF was not helpful here.
It is. I'll show you why. I'll show you why in a second. Another way of doing this, you can also do it with a linker for convenience. I can get the exact same functionality of exec stack by using the -z keyword exec stack in your make file for the linkage instruction. Okay, so if I look at the diff that I need to have in the make file in order for it to work, is that I just add to the LD flags the -z exec stack. And then I don't actually need to use the external application. Okay, it does exactly the same. What happens, what's the difference between the two ELFs? If I were to compare read ELF before having set the stack as executable and a read ELF after having set the stack executable, I would see that the GNU stack has the only addition is this E, which has been added to the GNU stack section. And the significance of E is exclude. So it's kind of minus. It's exclude stack from not requiring stack, from not requiring executable.
So it's execute.
So it's execute, but X actually, X means execute, not E. Okay. So this is the difference between before and after. Okay?
Sure.
So now I have the machine code on the stack, and this is what it looks like. Okay, and we saw that it works. Okay. Ooh, well ahead of time. Could have spent more time playing around with GDB. Okay. So this is basically where I wanted to get to. At the first stage, I have machine code running on the stack and executing execve, spawning a shell. Okay. Now I basically need to put the two together. Okay, we saw earlier how we intercept the flow. We saw how we're going to spawn a shell, and now we have to put these two things together to make the final shell code. So I'm going to modify my the application I'm using to develop this, the naive application which I'm using to develop this, to look a little bit more like what it's going to look finally. So I added the function vulnerable function. And what vulnerable function is, it's got its buffer which I'm going to overflow. Okay, and there's the call to str copy, which copies the source into the buffer. And this is where I'm going, and this is what I'm going to try and now trigger. Okay. And the code I'm going to, and what I'm going to do is, at first stage, before providing the input as an input to the process, to the application, again, for convenience, I will provide it to the buffer. I will declare it anywhere in the program, and just provide this buffer to vulnerable func. Okay, my execve, I will provide to vulnerable func. Okay. So this is the triggering strategy. Somewhere we have our shellcode. Okay, this is the implementation of execve. What we will do is, beyond the shellcode, we will, it's called address smudging. We don't know exactly where the return address is going to be. So we'll just write the return address many, many times with the hope that at some point we will also overwrite on the stack where the return address is supposed to exist. Okay. Where we're going to return to? Well, that we also don't know exactly. So what we're going to do is before the shellcode, we will insert NOPs. NOPs is hex 90, and we will jump somewhere into those NOPs. We don't know exactly where we're going to reach, but the idea is that the CPU will do a couple of NOPs and then ultimately reach our shellcode. So that's the idea. So if you look if this is the stack and this is where the return address actually resides, okay, and this is how our shellcode is situated on the stack. You see, it doesn't really matter if it's situated in this position, or a slightly higher position, or a slightly lower position. As long as we get it more or less right, we will overwrite the return address and jump somewhere into this NOP area, NOP, until we get to the shellcode and execute the shellcode. So that's the idea, that's the strategy, and that's what we're now going to try and do. However, there's a snag. And the snag is that it doesn't work on 64 bits systems.
Because of the returning address?
What in the returning address?
It's not 64-bit.
No, it is.
Yeah.
The problem is as follows. If this were a 32-bit system, then the address on the stack to which you want to jump would look something like this. On a 64-bit system, it looks something like this. But it's not really the number. What the number really is this. This is the return address. What's the problem with this return address?
It's not going to be copied.
Won't be copied. The same problem as we met before. So if I smudge the addresses with these, if I smudge my the stack with these addresses, then the first null terminator which we encounter will stop the copying and we will not override the return address. This is known and called ASCII armoring, and in 64-bit systems, they specifically designed things such that addresses have always got null terminators in them. There'll always be zeros within them. Okay, this is one of the protections that we have on 64-bit systems against this kind of attack. Okay, so if this was going to be my original scheme, I can't do this anymore. And what I'm left with, because if these are my return addresses, you can see that I'm not going to be able to overwrite the return address. The first zero I hit will stop the overloading. Okay, so what's going to be the new strategy with a 64-bit system? I'm going to have to be a bit more accurate, okay? I'm going to have to be more accurate, and I'm going to have to be able to hit the return address exactly, and I will not be able to do smudging, okay? I'll have to fill in with non-null terminator values, okay? The return address will be able to jump somewhere into the NOP area. It doesn't have to be precise, but where it resides on the stack has to be precise. One final snag before we get it to work. Anyone think of what problem is left to deal with before we can actually get this to work? The same family of problems.
I don't understand.
How to find the return address?
Remember what the first parameter is to my execve?
Array.
First parameter, string, containing, what do you have at the end of the string? Yeah, we have an null terminator at the end of the string. Okay, which we also have to get rid of. Okay, so the way we do that is we remove the null terminator, and as part of the shellcode that we write, before we execute execve, we replace this ff with an null terminator. Okay. And the way it will look is this. So if this was my code, I'm coming back to my pseudo code. So now what I will have to do is insert another instruction, which is to place a 0. Okay, sorry. Yeah. Okay. Place a 0 at RDI. RDI is a register containing the first argument. At RDI plus 7 /bin/sh plus 1 place is 7. Okay? And this code here at 03 is what will place the null terminator at the end of the string. Okay, now the code is ready. And this is what the final code looks like. Okay, so the final code in myexecve has got NOPs at the beginning. We're looking at from the lower addresses to the high addresses, of course. So NOPs x90, quite a few of them. Then we have the implementation of the shellcode, okay, with /bin/sh followed by an ff instead of by a 00. Okay, and here is the code. This is the code that changes that at runtime. Okay, and then we have non-null terminator padding, and the return address 00 will be our null terminator, but that's part of the address. 7f, ff, d3f0 will throw us somewhere into the where the knobs are.
How do you know that it will throw you up to where the knobs are?
Well, I would use GDB to get an idea of where I'm going to be. Now, I can't do this removed from context. If I were really trying to attack, it would firstly help if this were a naive program or an open source code which I could play around with. I would play around with GDB and get an idea of the distances, the sizes, and there'd be a lot of trial and error. Okay, it may not work. I may have to play around with the return address until I get it right. Okay, a lot of these attacks are based on the fact that you run them a few times with slightly different configurations. In the end, one of them works. So let's just see how that works. Okay, so here's my myexecve. No, what? In blue, but whatever. So here are our NOPs, quite a lot of them, as you can see, a large block of NOPs. Here the code starts. What's going to become the null terminator of /bin/sh, padding, and a return address. Okay, so that's myexecve in an array, which is simply passed to the vulnerable function. The vulnerable function copies it onto dest. Dest is only 256 bytes long.
So you need NOP more than 456.
Yes, you have to push.
Yeah.
Further up. Correct. Okay. And if we run it, so this is the content of myexecve, and upon returning from the vulnerable func, we're now running myexecve. So now basically all is ready. All we need to do is take myexecve and provide it as input. Put it in input as h.
And add the red exploit.
And add, well, the red exploit was a bit more work that I did. That's actually adding a PS1 key value environment variable. So I didn't pass null as a variable. That was just an exercise which I did, but there's a lot more work. There's a lot more work just to pass that. And you can't have spaces there because if it's spaces, then it regards it as two different arguments. And in short, next time. But it's less interesting because it's just more of the same. Okay. So here's the naive C program, and here's the input sh program. Because, okay, as often happens, because the naive C has changed, addresses on the stack may change a little bit. And when I ran the exact content that was in myexecve, I didn't hit the exact return address. So I had to modify the return address. Again, I work with GDB, saw where the correct return address is, and modified it. Okay. So now my program has become simply this. And input as h is this. And if I run it, we're nearly finished, guys. Yeah, it is working. Okay, I just rebuilt the application, the naive app, and it's now it's working. Okay. Okay, so basically that's it. A few more things I just want to mention to round it up. In a few words, defenses that we have against these kind of attacks. So this kind of attack, there's not one specific thing that we do to guard. There are a couple of things that work in conjunction, which today make it very, very difficult to issue this kind of attack, definitely on a 64-bit system. And I'm not talking about, that's besides the obvious of using strn copy rather than str copy. So one strategy is we saw W XOR X. We don't have a section within the ELF that allows both writing and executing. Okay, we saw that with the read ELF. We make stacks by default non-executable, but we saw that there are ways to get around that. Okay. ASCII armoring. We mentioned that. Addresses on 64-bit systems have got zeros in them, which make it difficult to do the address smudging. Okay, and there's one very important thing which I didn't tell you at the beginning. By default, all the addresses that we've been talking about now are, of course, virtual addresses. And Linux, by default, what it does is that each time it runs executable, it gives a different starting offset. Okay, so we know how the different offsets within the code are supposed to relate to each other, but we don't know the starting offset until we actually are loaded into memory and start running. So by default, Linux is always, every time you execute, it will start at a different virtual address, trying to dodge where it puts the return addresses each time. So if it worked for me once, the same code may not work again. Or saying a different way, if it didn't work once, it doesn't mean it won't work if I run it another 5 times. I might hit the return address. Okay, and this file proc sys kernel randomized va virtual address space controls whether or not Linux is going to behave in this way or not. So, of course, before I started the lecture, randomize. I put 0 in there. Okay, that's not the default value. The default value is 1 or 2. Okay. Again, if it were not 0, then it wouldn't mean that the attack wouldn't work, but it wouldn't work every time. So you'd have to run it a few times, and it's enough diligence and intent. Ultimately, at some point, it will work once, at least once. And the last defense I'm aware of is called stack canaries. By default, the compiler inserts extra code into our program such that before returning to a return address, it queries the stack and sees that no one touched it. Okay, and the way that's controlled is by default, there's a switch for the compiler, the C flag switch, called no stack protector. By default, it's not enabled. Okay, of course I enabled no stack protector because I don't want the operating system to query that I haven't done damage to the stack before returning. So if I build it like this, let's just run to main. You don't need to run to main. Let's just disassemble main. So disassembly. So what I'm doing now is disassembling the main code. This as main. That doesn't help me. Let's do an obj dump. It'll be clearer. Let me just see it here.
You just run?
No, it shouldn't work if I run it now. Naive.
Exactly, too.
Yeah, input it. SH. I get a, okay. Stack smashing detected. Okay. And I would expect to see vulnerable func.
So every return from a call function, we are wasting time on doing this.
Here we go, guys. Here we go. So coming back from vulnerable func back into main, vulnerable func and main are user functions, so that's why it's inserted in these in vulnerable
Is
func.
it our default compilation?
It's default, yeah, for sure. You see, we have stack check fail. Okay. So before returning, we have the call to check stack check fail. That's what caused me to segmentation fault now. Okay. But if I build it,
So we should remove it.
but if I build it, we should add this flag. If I build it with this flag,
We don't want this extra code.
like
We have no problem with security.
Exactly.
Not our.
It's bank. What does they care about security?
No, they
Our
need
responsibility.
right. Okay, so guys, now I built it again with that with the C flag inserted, and you see there's no longer a call to this. There's no longer a call to the checking function.
Again, I'm asking, is it going to improve our performance?
Yeah,
Okay, so let's try.
it's going to improve performance,
Let's try to see.
but it will decrease sales.
No, I don't think so.
No.
We are bringing it
Listen,
close.
check marks.
They wouldn't.
You fail check marks for lesser problems.
Really, checkmark will look for that?
Sure. If not, then they've got then they're not doing their job.
Yeah,
So.
I think an antivirus or a machine learning tool could easily trace these changes in the assembly code.
Sorry?
The adding of nopes or the adding of the stack smashing.
What about it?
All of these could be easily found by an antivirus or a machine learning tool, which saw it before. No, an antivirus, a deep packet inspection tool.
Well,
Deep
any
inspection.
antivirus that's got binary what we call binary signatures will be able to identify that your binary signature is different from the official one. And
Not even from the official one. Even if it's expected you run.
but you don't know
code,
exactly.
You
but
could see that it's a trace which.
It's difficult because this was my implementation, and other people can implement it slightly differently. And it's possible. It's possible, but there's some defenses. Okay, guys. So that's it for today.
Made it specially for us, or you had
I
something?
have to admit, I made it for my team at SanDisk about a year and a half ago. But I presented it once, and it's nice to have found another opportunity. So,
It was very nice.
Very impressive.
I learned a lot.
okay, guys. Thanks very much.
Thank you.
Thank you. Thank you.
Bye bye.
Bye.
Thank you. Bye.